Okay, so hello and welcome everyone to week 9 of interactive live sessions for the course on fundamentals of convective heat transfer, which is being instructed by Professor Amaresh Dalal of IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras, and like every week, we shall be solving problems together. So, without further ado, let us begin. So we shall dive into question 1 of today's session. This is regarding natural convection over a flat plate. So the question says that water flows over a vertical plate with surface temperature Ts equal to 60 degrees Celsius. The forced motion velocity above which natural convection is negligible is how much? This has to be found out. Now, the properties of water, the kinematic viscosity is given as 0.63 into 10 power minus 6 meter square per second, and the bulk modulus beta is given as 0.396 into 10 power minus 3 Kelvin inverse. Now, the condition over above which the natural convection becomes insignificant and forced convection becomes significant is that Grashof number over Reynolds number square equal to 0.1 or higher. So this is the limit that we're dealing with. So in that limit, what should be the velocity v? Uh, so this is in some sense the maximum velocity which could be there. Like if it's above that, then natural convection can be ignored and we can move on to forced convection kind of situation. So this velocity has to be found. The data given are the kinematic viscosity, bulk modulus.
Yes.
Yeah.
Okay. We can calculate Grashof number
Yeah.
and substitute it. Then we'll get Reynolds number, and from Reynolds number probably we'll get the velocity like that.
Exactly.
Okay. So Grashof number is beta z.
Yeah. G beta delta T.
Delta T LC cube. Characteristic length in this case it's vertical length h cube.
Let's do this then. So Grashof number. Grashof number by Reynolds number square is 0.1. Now, if we write down everything, Grashof number is G beta delta T, that is Ts minus T infinity into H cube divided by nu square. And this has to be divided by 1 over Re square. So V is U square, not U, here the velocity is V. So it will be V square L square divided by nu square. This has to be equal to 0.1 or greater. So nu square we can divide from here. L square would divide up this one. And if we write down this, we will get some, you know, expression for velocity. So I'll write down it over here, v squared. This would be equal to g. G is, we can take 9.81. Beta is given as 0.396 into 10 power minus 3. Then temperature difference is 60 minus 25. That is 35. And this would be divided by 0.1. Can you please help me out with the calculation?
Just a minute. 9.81 into 0.396.
That is 2.6 meter per second.
V or V square? Which one?
V. So V square is 6.79.
6.79. And then if we take square root, V comes out to be how much?
2.6.
2.6 meters. Sir, you are also doing the calculation. Can you confirm whether this one is right or wrong?
Just a minute.
Okay. So this is the answer. So V would be equal to 2.6 meter per second. So moving on, let me point out this. V could be this or lesser. If V is
Sir,
more, then forced convection becomes more significant.
Sir, can you check, Umit sir, can you check your answer again? I think it is something different. 1.16 I am getting.
Okay, let's do this. 9.81 into, okay, so 10 into 0.4. This would be around 4 into 3, 5 into this would 10 to the power minus 1, 10 power minus 1 minus 3, so 10 power minus 2. So this would be somewhere around 70, 140, 140, so 1.4 sort of thing, right? V square. Is V
That
square
35
above 1 point?
into
V
5
square
should
is
be there.
1.35 and velocity is 1.16 I am getting.
Yeah,
But
right.
that L should be taken, I think, sir.
Oh,
L keep
sorry.
upon
Yeah,
L, so that
yeah, I
into
forgot.
5 was be there. So
Correct,
that's
correct.
the
So there was one L over here. There should be
yes,
two.
into 5.
VL is how much? 5, na?
L is 5. Correct.
Okay, just a
So
minute.
V square becomes 1.35 into 5. How much is that? 6.79? Is it
It is 2.60, correct.
2.60? Correct. So what we did earlier was right. Okay. Okay. So I hope everything is clear regarding this question. We will
Yes,
move on.
yes.
Uh, move on to question number 2. So question number 2 says from integral solution of natural convection over a vertical plate, which was done in week 9. The ratio of average Nusselt number to the local Nusselt number at y equal to h is how much? So the question is there is a average Nusselt number and there is a local Nusselt number at y equal to h. What would be the ratio between them for which was obtained by integral solution of natural convection? Is it option A 4 over 3, option B 3 over 4, option C 2 over 3, or option D 3 over 2?
Is it 2 by 3?
Okay, any other answer? 2 over 3 answers. Anything
It
else?
is, I think, 4 by 3.
4.
4 by 3.
Okay, let's have a look at the correct answer, and 4 by 3 is the correct answer. So, average Nusselt number was found to be 4 over 3, local Nusselt number at y equal to. So, the ratio of these two will be 4 over 3. You can refer back to the lecture 1 of week 9. This integral solution and the results derived from it was discussed over there. This
Yes,
ratio was 4
yes,
over 2.
yes, I got it.
Okay. So moving on, so we move on to question 3, which says match the similar cases with respect to natural convection over inclined plane. So there are 4 cases given. One is hot side facing downward, hot side facing upward, cold side facing upward, or cold side facing downward. So similar cases as in, so the physics of the case might be different, but the math governing it is same. So which are the two pairs of cases which are similar? Is it option A 1 and 4 and 2 and 3? Is it option B 1 and 2 and 3 and 4? Is it option C 1 and 3 and 2 and 4? Or is it D none of the above? That is, none of the options that I gave here are correct.
I think it is B. 1 and 2 and 3 and 4.
And B 1 and 2 and 3 and 4. Okay. Any other answer?
Just a minute, sir. Match the similar cases with respect to natural convection over inclined plate.
So I can have a hot plate like this. Facing upward means the fluid will be over it, so the boundary layers would form like this. Or I could have a hot plate
Inclined
facing
plate.
downward.
It's
Inclined plate. Okay.
In that case, the boundary layer would form like this.
Just 4%.
On the other hand, I can have a cold plate.
none of the above is the answer probably
None
because
of the above.
I think
nothing is matching. Hmm.
No, one, I think hot wall facing up downward and cold wall facing upward. They should be similar.
So which option
Yes.
are you
So
choosing?
so first my consideration was I think wrong.
Okay, you
I
can
think it is
change your answer. What do you think now? Option
1 3, 1 and 3 and 2 and 4. C.
so option C. Okay.
No, sir. Umesh sir, actually in hot plate, the leading edge is at the bottom.
Yes. Similar they said. Similar.
Similar means
So let's have a look at the correct answer. The correct answer is option C. 1 and 3, that is hot side facing downward and cold side facing upward, are similar. And 2 and 4, that is hot side facing upward and cold side facing downward, are similar. Why is that? Let's have a look at these diagrams once. So,
facing upward.
so
3.
if I have a hot plate like this, which is facing upward, that is, this one is case 2. So in this case, we can see that uh, gravity works in this direction, and the fluid above it is receiving heat. Then I should try to draw this more clearly. I'll draw them here. Okay. So, so let's start with the option one, hot side facing downward. So the thing would be kind of lost. So this is the hot plate which is facing downward, and the fluid over here in this region near the plate, it gains heat from the flat plate, becomes lighter, and then tries to move upward. And gravity, as we know, is working in this direction. But due to the angle, the boundary layer doesn't spread as much as it would have spread if the plate was flatter. So in this case, the boundary layer would actually not be as thick as it would have been if the plate was flat. Similarly, so if we consider the corresponding case of the option 3, which is cold side facing upward, so in that case we will have the flat plate like this, and here the fluid near the wall that loses heat to the wall, to the solid, and then after that, that fluid would get heavier, the density would go higher, and it would try to go down. But here also, because of the inclination, the boundary layer cannot grow as much as it would have grown if the plate was flat. So in this case, the boundary layer will also be thinner than expected. That is why I am telling that these two are similar. And
Actually, sir, this concept we know, but what I am trying to think, similar in the sense कि here there is a difference of leading edge and trailing edge, na? But
yeah,
what they
see,
are talking
in,
similarity is
in
related
cold,
with
yeah,
thickness.
if it's cold, then leading edge would be upward because fluid is
Upward.
going down. And
Mm.
in case of hot plate, the leading edge is in the bottom, so it would go up.
So actually, I have considered that, and by that way, they are not similar. Here, the similarity is only for thickness they are talking about.
No, you can, that upward and downward is simply a matter of coordinate system. So I can take y this way and x this way for a cold plate, and
Mhm.
similarly for the hot plate, I can take y this way and x this way, and that way the maths that I perform would be exactly the same.
Yes, yes.
Okay,
Then it's okay.
and following similar argument. So if I go to case, okay, not three, sorry. If I go to case two,
Yes, 2.
hot side facing upward, then the boundary layer would actually grow much more than what it would have grown if the plate was flat. And similar thing for a cold side facing downward. In this case also, the boundary layer would be thicker than expected, thicker than if it were flat. So that's why these two are analogous. The case,
Then, yes, can we say that in the first and third case, the boundary layer growth is, you can say, prevented or obstructed by the plates?
yeah, due to the inclination of the plates, and here
Inclination of
it is
here,
more
they are not.
enhanced.
They are free. They are free.
It's
So,
just like pinching of the boundary layer.
so can we say anything about the average Nusselt number or average heat transfer coefficient between the two cases? Let's say,
In
forget about
first
the cold cases. Between one and two, which one would be higher?
first one
First one
First
count
one would be higher, exactly. And
because
why is that? Because the
modular thickness is less.
nominal
thickness.
thickness is less, so
Yes.
temperature gradients are more, so that would cause a higher rate of heat transfer. Correct.
But can we say that if first and third case, the heat transfer average heat transfer coefficient will be same
It would be similar, yeah.
if the
Given
surrounding
Yeah, given the temperature differences are same
is
and
same?
all other
No.
material
Okay.
properties are same.
So if the temperature difference is same and the dimensions of the plates are same, then
Correct.
the transfer coefficient will be same. Yes.
Exactly.
Directly speaking.
Yeah.
The same will be the case in the 2 and 4 also.
2 and 4 also. Just that the direction of heat transfer would be different. Like in
Yes,
2,
yes.
it would be from the solid to the fluid, and reverse for case 4.
Okay. Yes.
Yeah. Not only those average quantities, but even the velocity profiles and temperature profiles, they will also be same. Given that you have to keep those non-dimensional parameters same and the scales also same.
Right.
Okay. Okay. So moving on, between the two cases undergoing natural convection, which one would have a higher Nusselt number? Hot side facing downward or cold side facing upward? Case one, or case two, hot side facing upward or cold side facing downward. So this is, if I'm not wrong, similar to uh, 1 and 3 from the previous case, and this is 2 and 4 from the previous case. Did I do this correctly? Hot side facing upward. Yeah.
Hmm. Yeah, yeah.
So which one would be higher? Just
First.
discuss this now.
First.
First.
The first one.
No, not first one. The second one. No. So
Just one.
2 and no, I think
Hot side facing upward is
upward.
having less.
hot side facing upward is having less.
Less.
Yeah, correct. So I this coloring is wrong. So this one
This answer
is
is
the
first.
wrong answer. This is the correct answer. Hot side facing downward would have a higher Nusselt number compared to the other one. Okay. So moving on. So for natural convection over a sphere, where is the maximum value of heat transfer coefficient H? So
Theta 0.
0, 0,
0, 0.
0.
if we take a sphere which is at a higher temperature than the T infinity, it would set off natural convection currents like this. So I could do this a bit better. And theta I'm measuring from here. Theta is starting from here. So this is theta equal to 0 degree, somewhere 45 degrees here, 90 degree would be perfectly horizontal, and 180 degree would be here. So where would be the
0.
maximum? At theta equal to 0.
Yes.
And why
Yes.
is that?
Minimum boundary layer thickness.
Minimum boundary layer. It's correct. Okay. So moving on, we move on to another numerical type question, that consider a hot horizontal cylinder of length 1 meter and diameter zero point 0.2 meter, which is placed in cold air. So the temperature of the cylinder and its ambient both are mentioned. Calculate the rate of heat loss. Prandtl number is given to be zero point 0.7, and take Rayleigh number for the particular flow condition as 10 to the power 6. And the Nusselt number for a horizontal plate is for a horizontal cylinder is also given. So Please have a try at this one and let's see what the answer is. So 10 to the power 6 to the power 1 by 6. How much would that be? That would be simply 10 to the power 1, that is 10.
Yes.
And over here we have 1 plus 0.559 divided by Prandtl number, that is 0.7 to the power 9 by 16 to the power 8 by 27. We can simplify this a bit. So let's forget about air. Let's take any other fluid for which the Prandtl number is equal to 0.559. Okay. So in that case, this goes to 1. So 1 plus 1 becomes 2 and okay, square over here. So this can be simplified as 0.6 plus 3.87 over 2 to the power 8 by 27. The square of this thing. Can you please do this calculation and let me know what the value of Nusselt number comes down to be?
My answer is 14.63 something.
14.63. Can you please confirm whether this is right? Is it okay? This value of 2 to the power 8 by 27, how much is it? Roughly. Give me a rough value.
It's 14.1 I'm getting. This
14
particular
point something is the Nusselt number.
Yes.
Can you please tell me what 2 to the power 8 by 27 is?
2 to the power 8 by 20.
It is 1.22.
1.227.
1.22. So this would be roughly 2, I can say 2.6 square. It would be a bit more than 2. Okay, so this checks out. At least the order of magnitude is the same.
4.0. 14.
Yeah, so
There
now
is
we
another
have
number.
the Nusselt number to be equal to 14.63. And as we know, the Nusselt number is HL by K
K
equal
is
to.
not K.
By assuming thermal conductivity 0.025 for air,
Okay, so yeah, the value of K is not given. So K we can take as how much?
0.025.
Not 25. This is watt per meter square.
Watt per meter Kelvin.
Watt per
Meter.
meter Kelvin. Watt per meter Kelvin. Okay, so if we take this value, then we would get H equal to 14.63 multiplied by 0.025
Upon
divided by L. L is 1, no worry about that. How much does this boil down to?
sir.
So L should be diameter, no? Horizontal cylinder.
It is horizontal, it is diameter. If it is
Horizontal
vertical, it is
cylinder.
1 meter.
Okay, yeah, correct. Sorry, I'm wrong. Yeah.
0.2.
Point.
H is 1.82.
1.83. Rounding up.
So 1.82 or 3. Let's take 1.825. So here we got the value of H, and now simply Q we can calculate as H
57.42.
delta T. So H is 1.825 area is L into pi into D
into 50.
into the temperature difference is 50.
18.20.
So,
57.42.
so this becomes 25, right? 25 into pi into 1.825. How much is it?
Right.
57.3342. 57 point something.
57 point something. Uh,
33.
is the other answer also matching?
No, it is not 57, I think, sir.
57 point something, is it? No?
Yes, yes.
No,
57.42.
no, I'm trying to confirm with the other person. Are you getting the same answer?
So 1.83 into point 2 into, yes,
250 into pi.
3.1. Yes, 57.5, right.
57 point something. Okay. We will work with this. This is the rate of heat loss from the horizontal cylinder. Okay. So in general, not only this problem, in any problem, there are, you'll have to identify the nature of the problem, and there are multiple correlations available for different cases. So, which case to use first, identification of that is important. Then we need to calculate the relevant dimensionless numbers which are required. So that could be Rayleigh number, Prandtl number, and Grashof number also appears in certain cases. So using those, we can find the Nusselt number. And once we have found that, the rest of the steps are actually common for all cases. So after getting Nusselt number, we will have to calculate H, and then for calculating the rate of heat loss, we simply go back to Newton's law of cooling, Q equal to HA into the temperature difference. This protocol is common for a large class of problems. However, those finer details, the actual correlation that we use might be different from case to case. But otherwise, this flow of steps are the same.
Yes, in the last assignment, what they have done, sir. Now this is the proper question.
Hmm.
But in the last assignment, they have asked some two numericals where the correlations are not at all given.
Yeah. So
So
either
different books are having different correlation, and in correlation itself, there is a 10% variation. Who discovered that correlation?
different correlations might have.
So mm, again, in
Post
exam,
those
that's
queries, like I'm really hopeless in this situation. Post those queries and hope that they get answered. They get addressed somehow. So if there are no more questions regarding this, we will move on.
yes, yes.
We'll move on to question number 7. That by integral solution of natural convection over a flat plate, the velocity profile, if assumed as a fourth order polynomial, it's given as v over v naught, where v naught is some characteristic velocity, equal to x by delta into 1 minus x over delta square. So, knowing this profile, find out the location of maximum velocity.
It is delta by 3, sir.
So basically, we have this flat plate like this, and we have a thermal boundary layer as well as a velocity boundary layer forming. So the velocity boundary layer is something like this, where this is distance from the plane. Now, as we can see that there is it is zero at the wall due to no slip condition, and it's also zero in the far field due to the quiescent medium. But so from here we can see that there must be a maximum somewhere in between. So this finding out this distance is important.
So we can do daba v by daba x is equal to 0, and by that way we are getting delta by 3.
So dou v dou x can be put to 0. So
Yes.
since we know this, so we can say that okay, I'm taking v naught out of the equation. I can simply multiply it both sides, and since 0 is there, it will vanish. So okay, let's write down v separately here. V is v naught over delta, and okay, I'll keep this delta in between only. So this becomes 1 minus 2 x by delta plus x by delta squared, and this whole thing would be multiplied by another x by delta. So this would essentially become uh, x by delta minus 2 x by delta squared plus x by delta cube. Correct. So now if I differentiate this with respect to x, so and I'm leaving out b naught outside, so this could become 1 over delta minus 2 into 2 4 x by delta squared, and over here this becomes 3x squared by delta cubed, and this has to be put to 0. Now let's multiply this whole thing by delta cube, and let's neglect b naught. So that's how this equation boils down to delta cube, sorry, delta squared minus 4x delta plus 3x squared equal to 0. Correct. Now, oh, sorry. What am I doing? It's squared in between, not outside. I thought it was whole squared. Extremely sorry.
Sir, it is actually in the problem, in the session, the videos, it is whole square. The whole square is taken. 1 minus x upon delta whole square was taken in the videos. Huh? If this problem is different, then we can solve it differently.
Sorry, I'm not able to. What are you saying?
In the videos, that term was taken as 1 minus x by delta the whole square in the videos, and the problem was solved.
Is it so? Let me
Yes,
check quickly.
in the videos,
In the
and the
lectures.
answer was x is equal to delta by 3
Okay.
in the video lectures.
I'll check once if you can.
Yes, it is 1 minus x by delta full square, bracket square.
Okay. This has been a huge mess up from my part. So forget about this 2 over here. This is outside.
Yes. So what you did previously, that was correct
Yeah, it
actually.
was similar. I had that in mind. That's why.
Yes.
Yeah. So this would be sorry. This would be v naught into 1 minus 2 x delta plus x over delta whole square. And this thing multiplied by x y delta. So once again, it would become v naught into x y delta is 2 x y delta squared plus x y delta cubed. If we do dou v dou x, then would be sorry. For maxima, dou v dou x has to be 0. So this v naught into 1 over delta minus 4x by delta squared plus 3x squared by delta. This has to be equal to 0. Now simplifying this, it becomes delta cube minus 4x delta plus 3x squared equal to 0. Now we can factorize this. So how can we factorize? We can take 3x delta over here and x delta over here plus 3x squared equal to 0. So if I take delta common from here, sorry, this was delta
It is the
squared.
square. Delta square is it?
Squared, sorry. So if I take delta common over here, this becomes delta minus 3x. If I take minus x common here, it becomes delta minus 3x once again. So it boils down to delta minus x or delta minus 3x equal to 0. Now x equal to delta cannot be the correct answer, because that's where we are assuming that it again becomes zero, the velocity. So the other answer must be the correct one. So from here we can get that x equal to 3, sorry, x equal to delta over 3. This is the location of the maximum velocity. Okay. Now, let me ask a bit more fundamental question. Like, if I'm sure you have gone through the videos, so there we saw that while considering the velocity profile, we assumed a fourth order velocity profile, and in case of temperature, a third order polynomial was assumed. Why this difference? Why are we limited to fourth order or third order only? Can you think of any reason why we are taking such orders? Is my question clear, first of
Yes,
all?
sir.
What am I asking?
No idea, sir.
Boundary layer concept somewhere.
Yeah, of course, we're discussing boundary layers only, but why is that? Like, why 3 and why 4? Where do we get those numbers? So, maybe, temperature, we took, we took this one, T being a function of both x and y. We took it
Sir, can I
in
try to answer this question now? Based on the temperature profiles, if you see, there is a lot of variation in the velocity profile as compared to temperature profile, because it increases from the plate surface to reaches to maximum value, again decreases, reaches to the V infinity.
So
But
that
in
makes sense
which
that
is
gradients are more rich, so we should take,
yes,
more terms of
higher order
velocity.
polynomial will taken, and in temperature, in case of temperature, just go on decreasing or
Yeah.
increasing based on the temperature difference. So
It's monotonic and it's non-monotonic, so taking a higher
lower order,
polynomial would make more sense. But
yes,
then, why should we stop at 4? We can take up to fifth order, sixth order, seventh order as well,
yes, that that I don't know.
right? Uh, we took something like this. Temperature profile, and for the velocity profile also similar. Similarly, we took some P1 of plus P1 of yx plus P2y square and P3y. This is Q. So what actually limits us up to the third order or fourth order is something else. That is the number of boundary conditions that we have available. So it is true that the variation of velocity is more rich as compared to temperature, having more terms would make sense, and paint a more clearer picture. But is what we desire. But what we get, what we can do, is actually limited by the number of boundary conditions. Temperature has 3 boundary conditions. For those, we know the temperature at the bulk. So this is at x equal to 0. We know at as x tends to infinity, T tends to be infinity, which is temperature of the ambient fluid. And sorry, the third boundary condition, we know that at x tends to infinity, dou t of dou x has to go to 0, since there is no gradient in the far field. But in case of velocity, we have 4 boundary conditions. What are those? At x equal to 0, we know that the
V is
velocity
equal
would
to
be
0.
0 from no slip. Uh, as x tends to infinity, we again know that v would be equal
Zero.
to 0, the viscous fluid. Similarly, tends to infinity, dou v dou x of shear stress would also go to 0. Apart from all these, we have actually another boundary condition as well, which is called a derived boundary condition. That is, at x equal to 0, we know the value of dou t, dou 2 v dou x2 to be equal to minus g beta by E1 into temperature difference. So where did we get this from? We got this from the Navier-Stokes equation, where we put the value of all other terms, and then only this term remains, and the value of it becomes this. So if we recall, so we found dou v dou x dou v dou y is equal to
dou t v by dou s
v by x square dou by dou y square as opposed to now instead
dou incident.
this was g beta and this delta t.
Yes.
So now at x equal to 0, u goes to 0, v goes to 0. This is due to no slip boundary condition, and this is due to no slip boundary condition, and this is due to no penetration boundary condition. Like if there is a boundary, then slip boundary can cross it. So the left hand side goes to 0 entirely. And another thing is, another assumption that we take for boundary layer is that this dou 2v dou y is much lesser than 2v dou x2. This we have shown multiple times by scale analysis. We put this to 0 as well. What it means dou 2v dou x2 as minus g beta delta divided by these are the same. So this we can use as an additional boundary condition, and that allows us to make the velocity profile as a fourth order polynomial.
Okay.
Makes sense?
Yes.
So this was the last question of. Thanks a lot. If the session went really well, let's meet again next week.